Okay, I think we know the deal by now. Advent of code, day 22 in Rust. Let's get into it. Today's problem is called Reactor Reboot. Operating at these extreme ocean depths has overloaded the submarine's reactor. It needs to be rebooted. The reactor core is made up of large three-dimensional grid made up entirely of cubes, 1 cube per integer three-dimensional coordinate. Each cube can be either on or off. At the start of the reboot process, they are all off. Could it be an old model of a reactor you've seen before? Okay, so they're referring to like an older Advent of Code problem from last year. To reboot the reactor, you just need to set all of the cubes to either on or off by following the list of reboot steps, your puzzle input. Each step specifies a cuboid, the set of all cubes that have coordinates which fall within ranges for x, y, and z, and whether to turn all of the cubes in that cuboid on or off. So, for example, given these reboot steps, on, x is from 10 to 12, y is from 10 to 12, z is from 10 to 12. Okay, so there's a series of kind of like binary on and off steps. The first step turns on a 3x3x3 cuboid consisting of 27 cubes. The second step turns on a 3x3x3 cuboid that overlaps with the first. As a result, only 19 additional cubes are on. The rest are already on from the previous step. The third step turns off a 3x3x3 cuboid that overlaps partially with some cubes that are on, ultimately turning off 8 cubes. The final step turns on a single cube. After this last step, 39 cubes are on. The initialization procedure only uses cubes that have x, y, and z positions of at least minus 50 and at most 50. For now, ignore cubes outside of this region. Okay, so on and so forth, the last two steps are fully outside the initialization procedure area. All other steps are fully within it. After executing these steps in the initialization procedure, 590,784 cubes are on. Execute the reboot steps afterwards, considering only cubes in the region 50 through 50, negative 50 through 50, negative 50 through 50. How many cubes are on? Okay, so let's just go for it. 50 to 50. So each, basically what we're saying is that the range of the sort of three-dimensional area that we care about is 100 cubes wide on each dimension, which means if we were to materialize this as like an array or something like that, it would be 100 times 100, which is 10,000 times 100, which is 1 million elements, 1 million Boolean elements, or 1 million bits. That doesn't actually seem like too much to just like fully model, although it might be slow to iterate over and count things out of. So perhaps what we can try to do is just keep track of all the cubes that are on, which would be a set of 3 tuples of coordinates that are on. The trick with that is if we run into anything in our input that covers a huge volume, that data structure could get really big. And the way that we would update that data structure is we'd have to iterate over every single thing and determine whether it should be on or off, right? So I'm just taking a look here. You can see that these later instructions start to cover really, really massive volumes. However, we only care about cubes in this sort of like central range of 1 million cubes, or central volume of 1 million cubes. I think that means that some of these instructions aren't going to be relevant to us. And in some cases, we may want to detect the situation where we're actually encompassing the full volume, and we essentially have to reverse the sense of whether we're keeping track of things that are on or keeping track of things that are off. Well, let's just dive into it. I think parsing this will be actually a little bit of a challenge. Not a challenge, it's just going to be kind of annoying, I'm going to say. So I'm going to start by just pasting in our input, and let's just do a parse first of all. How are we going to describe these instructions? Well, it's either on or off. Let's just call it a Boolean. If it's false, it's off. And then we're going to have a range. We're going to have a minimum and maximum along every dimension. We could also model this as tuples. We could also actually use the range data structure in Rust. I'm gonna go for tuples. And then I think this may be a day where I'll be served by just doing regular expressions. Gosh, I really hate using regular expressions. You could say I'm almost a little bit allergic to them because I think they're annoying to work with. Well, why don't we actually just try to do a parse of a single line? And see how far we can get. So we get a line, or a single line. Let's just call it line. And we're going to return an instruction. For this instruction, let's also just derive some standard traits that I think we're going to need. Really, it's just debug and clone for now. We may need copy in a second. Okay, so if the line, so let's just say let on equals if the line starts with on, then it's true. And then also, I think we want to update string, right? So let's say string equals, or line equals line.strip prefix on. I think the other thing we can just do is like maybe do a slice expression. So we basically want to start with the 0, 1, 2, 3, 4th character, or the 3rd character going forward. Otherwise, line equals 4 ... and it's false. Okay, so now we know whether it's on or off. We can return an instruction. Using this variable that we just parsed. Okay, so now once we've parsed off that prefix, we've got these 3 tokens. And the first one will be about the x coordinate, the second one will be about the y coordinate, the third one will be about the z coordinate. Let's go ahead and split this line along commas. Actually, let's split along the string comma so that our result is a series of strings. So let's deal with x first. We know that the first 2 characters we don't really care about, so what we're going to do is let's make another function. We're going to return an i32 tuple, and what we're going to read is something that looks like this. Let me just put some examples of what this parsing is actually doing. Just throw a couple examples in here. Let's get enough in there. Okay, so now let's parse this range. What is it complaining about here? Okay, that's fine. I just haven't finished filling out this structure here, but we'll do that in a second. In fact, what we can do is we can just say x is equal to parse range of tokes.next.unwrap, and it will be the same for y and the same for z. Now all we have to do is just fill out this function here. So first of all, we are going to ignore the first two characters. Because we don't really care about that. And now we just need to split this into two expressions, two strings that are divided by two periods. And then we just return tokes.next.unwrap.parse. Parse.unwrap again. And that's how we're going to parse it. I think it's complaining because we're not treating these as mutable. That's fine. When we say mutable, we're just saying that this local variable can be reassigned, which is what we're doing here. It's not going to actually change the content of what we're pointing to, because this is not a mutable reference to a string. That distinction actually took me a little while to get my head around. Okay, so let's actually just let's run this sucker. Did I not? My main function is up here. Okay, cool. So let instructions. Let's just make it a vector of instructions equal to get input dot lines, and we map that into parse. Well, we'll just pass parse instruction, right? And we'll collect that, and we will just debug print this. Okay, now let's run it. Okay, so our last instruction is an off, and it goes from 18,924 to 37,949, negative 14,489 to 3,903, negative 89,594 to negative 67,779. So this is actually an example of a sort of an instruction that I think we might be able to just ignore completely. Again, we're only constraining our consideration in the central cuboid that contains like a million objects in it, and this particular instruction we can kind of ignore because it just doesn't overlap our central cuboid. So one thing that we can do is actually go through our instructions and weed out the ones that don't overlap the range that we care about, right? Okay, so let's give that a shot. While we're doing this map here, I'm going to add a filter. And we're going to have an instruction here. And we're going to say, filter, we basically are creating a closure that returns true if we want to keep this item. And so we just need to make sure that we have an overlap on the X range, we have an overlap on the Y range, and we have an overlap on the Z range. Let's make a little function that does that for us, right? returns a Boolean of whether these two overlap. I believe the overlap is going to be inclusive because these ranges here include the cuboid at, for example, 10,239, and they include the cuboid that on the y-axis that is at 18,040, right? So to do an overlap, boy, this is always like slightly trickier than I expected to be. I believe that the minimum on one of these arbitrarily has to be greater than or equal to, has to be less than or equal to the maximum of the other one, and vice versa, right? So what if it's something like this? A dot 0, which is the minimum for A, needs to be less than or equal to B dot 1, and A dot 1 has to be greater than or equal to B dot 0. Let's actually align all of our operators. So there are different kinds of overlaps that we can account for. Like we could have something like this. We could also have something like this. That's one case. Yes, I realize that like Rust probably has something for range overlaps, and maybe I should have just used a range. But you know what? This is actually a little bit more interesting of a problem to think about, right? And I like trying to work from first principle. Then okay, so these are like basically two overlap cases. We could have a case where A completely subsumes B. We can have the reverse of that. And then we can have some disjoint cases, right, where they don't overlap at all. And among those, I think we pretty much just have these. And the reason why I have these kind of like reflection cases along the y-axis is because A and B, we don't know which ones are which in this case. So the criteria I'm saying is that the minimum has to be less than the maximum for both of these, right? So the minimum of one has to be less than the maximum of the other. So in this case, the minimum is definitely less than the maximum. And this minimum is less than this maximum. So that's taken care of. In this case, this minimum is less than this maximum, yes. And then this minimum is less than this maximum, yes. Okay, that's done. This minimum is less than this maximum. This minimum is less than this maximum. Okay, that's taken care of. This minimum is bigger than this maximum, and this minimum is less than this maximum. Sorry, not bigger, less than that maximum. Okay, so far, all of the overlap cases are covered here. Now let's talk about the disjoint cases. This minimum is definitely less than this maximum. And this minimum is also definitely less than this maximum. Okay, so I think this is actually not sufficient. I'm sorry. This minimum is not less than this maximum. I switched what I was highlighting. So actually, I think this logic is correct. So in this case, this minimum is definitely less than this maximum. However, this minimum is definitely not less than this maximum. Okay, so I think we've got our kind of like overlap criteria here. And since we're including the edges, we're including the bounds, these are less than or equal to's. Okay, so we had a filter in our main function. It's funny, I'm kind of reversing the order that I write my code normally, where I usually put all the supplementary functions at the top, and then I put the main logic at the bottom in the main function. But it looks like I kind of went the opposite direction here. So I think what we want to do here is we are returning we want a range overlap between instruction.x and negative 50, 50. And we just want this on every single axis. Range overlap y and range overlap for z. You are complaining why? Oh, okay. If I do this, it seems like the dot will immediately dereference our instruction member variable into a non-reference, which is interesting. Okay, so that's our filter function. I am actually interested to know how many instructions actually get filtered out. So what we can actually just do is print out instructions.length. And we can just compare that to the number of lines in this, this input file. Wow, there's only 20 that matter. That's super interesting. Yeah, I mean, just looking at some of these, this one doesn't matter because it doesn't overlap that center area. This one doesn't matter because it doesn't overlap that center area. This also doesn't matter. I guess a lot of these ones just don't matter. And it's almost to the degree that I'm not sure if I'm reading this problem correctly. But you know what? Let's just go ahead and run it and see what happens. Okay, so we actually have to write our actual business logic here. And that business logic will be, let's just create a set. And let's just say, let's just call it active, and it's going to be mutable. It's a hash set. And then for instruction in instructions, we're just going to go over every single instruction now. We're going to go for x in instruction.x.0 all the way to instruction.x.1, for y in instruction.y.0 all the way to instruction x.y.1. And we're going to do the same thing on the z-axis. And then if the instruction is on, we are going to insert into our set or add x, y, z. But if it's off, we are going to remove this. Add is called insert. Boy, this sort of like IDE that I'm using, which is Rust Analyzer inside VS Code, it's so aggressive about auto-importing some things. But when I type the word hash set, it doesn't auto-import it for me, which is a little bit annoying. I believe it wants me to pass a reference in for the remove function, and I think that's going to be it. So at this point, we now need to actually eliminate entries that we don't care about, that are not in that sort of central cube. So actually one thing we can do here is just restrict these bounds to negative 50, 50, right? So I'm going to do something really, really ugly. So this is the maximum. It's the max of either the lower x bound or negative 50. And I wonder if I should just do this in a map here, right? We're filtering out stuff that completely is out of bounds. And then really we could kind of just restrict what we actually care about here, right? The other thing we can do, yeah, see, here's an example of like the language tools just like adding something I totally didn't need and yet I had a hard time understanding that I wanted a hash set. It's kind of annoying. I wonder actually if in our parsing here we can actually just like refuse to parse the instruction if the range is not where we want it to be, but I think maybe that's too much work for this parsing thing. So instead what I'll do is let's map over our instruction again. And what we're going to actually return is a new instruction, clamped, and instruction.x.0 equals, or rather clamped, and this is going to get very repetitive and boring. We're going to return clamped at the end of this function, but we need to copy and paste this a bunch of times. It's going to be the min. Instead of x's, we have y here. And instead of x's here, we have z. Okay, so this will basically update our instructions to clamp them to the area that we care about, which means I don't have to worry about it right here. I just need instruction.x.minimum0, which is the minimum, all the way to this. And I believe this should now be back to where we want it to be. And at the end, we just print active.length. Okay, I'm just going to go ahead and run it on our actual input here. We'll see if it finishes or if it's just terribly slow. 580,012. Okay, so we got that answer correct. That's nice. I'm going to go ahead and add the code that we just wrote to Git. Nice. Let's copy that directory into part 2, day 22b. And update the toml file, cargo.toml file, just to make sure that it compiles. And it does. Nice. Okay. We're going to reload the editor real quick. And we're going to open up part 2's source code. Now that the initialization procedure is complete, you can reboot the reactor. Starting with all cubes off, run all the reboot steps for all cubes in the reactor. Okay. After running the above reboot steps, this giant number of cubes are on just for fun. 474,140 of these cubes are also in the initialization procedure region. Starting again with all cubes off, execute all reboot steps. After considering all cubes, how many cubes are on? Okay, so this is fun because basically our filtering that we're doing here is no longer relevant. So essentially, we can just get rid of the filter in the map here. And if we tried to run this right now, my guess is that it just simply won't. It simply won't run, right? We're expecting some like gigantic value. We're expecting some gigantic value here, and what that means is the size of this active hash set is going to be just like way bigger than what a ton of computers can store, right? So we wouldn't even be able to like run processing on it in any reasonable amount of time. So we need to be a little bit smarter about the way that we're doing this. So I think one thing we can try to do to make this a little bit more tractable might be to go over each rule and see pairwise if some of these cubes are completely subsumed within other ones. Right. And there's going to be a lot of back and forth, right? And so we want to see if there's anything that will like just totally cancel out something else, and then potentially split these instructions into multiple smaller instructions. So rather than doing this Boolean math on the entire space, we're going to do the Boolean math of these things against each other. And that's going to be a little gruesome, I think. We're basically needing to pair ons and offs. Like if there's an on, I want to just compare it to my off. Compare it to an off, and just like for example, if an on completely subsumes an off, we can get rid of the off entirely and then split the on into a bunch of smaller chunks. And the splitting part is going to be the fun. It's going to be like a fun piece of arithmetic. So what if I actually converted my instructions into ons and offs, right? So this might be a case where I want to do some clones. Ons is a vector of instructions. And that's going to be equal to instructions dot map or filter ins dot on. Probably need to make this an iterator. Instruction dot on dot map, and we're just gonna do instruction dot clone and collect those clones. Actually, I think we can just do cloned here, which should do the same thing. And our offs. Oh, there's no off, it's just not on. We're still probably going to do this, but the instructions that we're going to end up caring about are going to be a lot smaller than these giant things. Okay, one other thing that we should notice is the order of these. Actually, the orders do matter. Okay, so that's interesting. The reason why the ordering matters is that you can't just process an off. You can't just process an off and then another off consecutively, because it's not going to change anything. Okay, so I need to think about this a little bit more. This thing that I did with the filtering is not going to make any sense. I wonder if knowing the volume of these would help at all, right? We could calculate the volume that the instruction covers pretty trivially. And if the volume of them is larger than, like, basically maybe the things that we can be tracking are either the ones that are on or the ones that are off. But we don't know what it is just yet. And if the volume of this instruction, which is on, let's say we're tracking the ones that are on, like what we have here. And then we get to an instruction that turns a bunch of them off. Or really, that turns out a bunch of them on. Maybe what we start to care about are just the ones that are off. But that doesn't make sense because they're off by default. There's like an infinite space of off ones. So I can't do this flipping thing that was a solution to a problem from a couple days ago, but I don't think that that's necessarily relevant here. All right, I want to go back to the idea of like maybe somehow trying to reduce the size of these things or combine them somehow. Like, is there a way to know whether some of these are just completely subsumed within the other? Let's just take a look at the input for day 22. So I'm just going to highlight this number here and see if do these numbers reoccur anywhere. Like are like do we have any regions that are just touching each other or enclosing each other? Somehow I don't think that the problem is going to be that kind to me. Yeah. This is just kind of like a random sampling. It's not very rigorous. Okay, so these are all kind of disjoint. They're kind of floating everywhere. So there's no, where I was going with that is I was wondering, is there an easy way to just merge these together? Although merging them together technically doesn't necessarily make this easier unless they all merge into one giant thing. If I have two consecutive ons, let's just go back to the merging idea. Do they merge to anything that's useful? And maybe this is actually a point where I would like to start to draw things just so I can visualize this. So let me get this Rube Goldberg of a drawing system set up.
5 minutes later.
Okay, I'm back from my quick break. I wasn't able to get my tablet sharing directly to my computer, but we are going through the magic of the World Wide Web and using a tool called Miro, which I think is pretty good for sort of, collaborative whiteboarding. And so I'm collaborative whiteboarding with myself. I don't think it's as easy to read or as easy to use as using my tablet directly, but I think it'll get the job done. Okay, so the problem we're trying to solve right now is that previously we were keeping track of every single voxel in our 3D space, whether it was on or off. And that's just too expensive to do when these instructions cover ranges that include tens of thousands of voxels on each dimension. So perhaps what we should just be trying to do instead is we'll keep lists of volumes of voxels that are active, right? So if we look at the source code that we've got currently, right now our active item is just a single voxel, a single three-dimensional coordinate. But perhaps instead what we should actually be doing is a volume, right? And a volume actually just looks like this. And maybe what we just need to be doing instead is we should be iterating over volumes and just seeing if we'll keep track of all the volumes that are active, and then do some subdivision of these volumes if they overlap with an off instruction, or if they're consumed completely by an on instruction. It's a lot of finicky code, but ultimately it is relatively straightforward. It's funny, I brought up my tablet, but actually I think what I'd like to do is a little bit of programming first to just get us into shape. The first thing I'm going to do, it looks like I'm holding down the right-click button somewhere. I think maybe on my laptop. I'm running out of space on my desk. Let me just move some stuff around. I have a very, very small desk in a very, very small apartment. So let's do something like this. Struct volume. And it's going to look exactly like this. And in fact, maybe what we can do is rewrite our instructions in terms of volumes, right? probably going to want to do overlaps here. Okay, so now we have volumes. None of this code's going to work anymore, but it's okay because essentially our hash set is going to be hash sets of volumes that we need to turn on, right? And so our general algorithm will be something like if the instruction is an on instruction, we will want to add a volume that is equivalent to the volume in the instruction, but we also want to make sure to account for the fact that it may overlap and merge with volumes that already exist inside of our active set. So how do we do a merge operation? If we have an off instruction, what we're going to do is we're going to iterate over volumes and split them. With the instruction.volume. And this will be our general algorithm here. And then what we can do is once we're done, we'll just do this. Let total volume is equal to active, and let's actually give active a type. Active is just it's not a set, it's a vector of volumes now. Active is just going to be, we're just going to add up everything, right? V accum plus v dot volume. And that's it. And actually volume, I'm going to make a method. I think that's like a relatively easy thing that we can do here. Impl volume, fn volume, it's a reference to self, returns an i64. And maybe we can start to make everything i64s here. This will just be x.1 minus x.0 plus 1. This is the number of cubes along the x-axis times the same expression, but we're going to use the y-axis instead. And then we're going to use the z-axis. That'll give us the volume. And then our answer will just print the total volume down here. So I think this is actually a reasonably simple algorithm in concept. But we need to actually, the devil is in the details. This merge is tricky, and then this sort of splitting is tricky. So let's actually try to do some form of merging. So fn add volume to a vector of volumes. Vols is going to be a mutable reference to a vector of volumes. And the new volume is, let's just call it to add. is, let's just make it a volume, and we'll clone it. And then we're actually mutating this vector, and that'll be the outcome. So it's essentially return value of void. Add volume, active, and then to add is the instruction dot vol here. And we could just make this a reference. And then we could do remove volume similarly. Semicolon, semicolon. Okay, so this is the structure of our program. But we do actually need to write this out now. What are you complaining about here? Oh, I'm missing a colon, and that should do it. Cannot find X in the scope. There's some problems. Let me just go ahead and resolve this. Oh, these are all self dot. So every open parentheses, we're gonna replace with a self dot, and that should clear our problems. Found tuple I32, I32. Oh, it's because all of these things need to be I64 because I changed it all. Okay, and then we have a bunch of unused variables. Actually, these ons and offs, it's a bad idea to begin with. And then I think the only thing it's complaining about now is that we're not using this range overlap function, and we are not using, we haven't implemented add volume and remove volume, so we have some unused arguments here. I feel like remove volume might be the easier one to do. One of the things we can look at is if we're trying to remove this volume from this set of volumes, we want to find the volumes inside this vector that to remove overlaps with, right? And then either we're going to completely remove that volume, or we're going to split it based on its difference. So we need to be able to say, I'm going to subtract this volume from another volume, and it's going to return a vector of other volumes, right? And that subtraction may also be something we need to do in add volume as well, because if this volume that we're adding is like way bigger than a particular volume in here, we may want to, but it doesn't overlap completely, we may want to split the pre-existing volume. And I think that's a similar thing, and we may want to do something similar in reverse. I'm getting confused by the words volume, because volume both refers to a scalar quantity and then also this complex data structure. So what I might do is actually rename this to cuboid. And I actually think I might be missing a particular fact. The cuboids here are not just arbitrary ranges. They are cubes, right? They have the exact same dimension. They have the exact same magnitude on every dimension. And I think that's correct, right? 1 plus 44 is 45. 6 plus 40 is 46. 34 minus 20 is... So I'm wrong, actually. These are just rectangles. Why was I confused by this? cuboid, the set of all cubes that have coordinates which fall. Okay, so it's basically just the set of cubes that fall within a particular range. Okay, that was a bit of a red herring. So, but where I was going with this is I just want to rename the word volume to cuboid just to know that we're describing a shape. And that way, now when I say the word volume, I'm really just talking about the scalar quantity, the volume, right? The three-dimensional area, as it were, or the three-dimensional magnitude. Okay, so let's talk about remove first. Maybe this is going to be the easier one to think about. So I wonder if a vector is going to be, it's going to make this a little bit challenging. What we can actually do is return a new vector of the cuboids that we care about. That's another thing that we can do, and rather than mutating the original one. And that may be a little bit easier for us to think about. Okay. So our result is a new vector, and we're going to return that result. And chances are we're going to have a similar pattern up here in add. So I'm just going to do that here just so the type checker doesn't yell at me for not returning the right value. So now what we're going to do is we are going to iterate over the cuboids and see if they overlap with this. And there's two senses of overlap. You can have a partial overlap, or you can be completely subsumed by to remove. And if that's the case, then it's actually easier when it's completely subsumed, right? Okay, so with cuboids, maybe one thing we can do is we can check for overlaps trivially. And self and the other is a cuboid of the same type. This is a Boolean. And now we have this range overlap function that we never used before. And so what we can do is like actually call it now. We're going to return range overlap of self.x and other.x. We need a range overlap on all ranges, or otherwise they're disjoint. On all dimensions, I'm sorry. Okay. Range overlap functions never used. Well, I'm using right here. Oh, it's complained that I never call overlap. So it's like transitively unused. That's a kind of cool feature, and yet at the same time maybe a little bit annoying as well. So we're going to iterate over our input cuboids one by one. I might just call this source. This is where we're coming from. So for C in source.iter, if to remove overlaps C, or it doesn't overlap, we'll just continue. So what are some cases? If C completely encloses to remove, then we're done. No, we're not done. This is the removal case. If C completely encloses to remove, split C into multiple chunks, add those chunks to result, and then break. If to remove completely subsumes C, don't add C to don't add C to result and continue. If to remove and C are disjoint, maybe this is the first case. Just add C to the result. So actually, if they don't overlap, this is the disjoint case. The result, we're just going to push C onto it. Maybe we want to actually consume. We want to actually move the previous cuboid in there, the vector of cuboids, so that we can push. We can take ownership of that value. Yeah. Because we don't want to clone. We just don't care about. We don't care about this previous version. So what this is actually going to look like is that our active is going to equal this, or active is going to equal. So we're going to move it either way, and so we can actually do something a little bit like a ternary operation. If we get rid of these semicolons. Is that better? I don't know. Okay, so if C and if to remove and C are disjoint, just add C to the result. That's this case is. If to remove completely subsumes C, don't add C to result and continue. Let's call this Fn encloses. And let's make a utility function range encloses that sort of resembles this other one. And so this one, for enclosing here, we want to actually return a.0 is less than or equal to b.0, and b.1 is less than or equal to a.1. And what this is going to say is that basically a completely encloses b, or either completely or perfectly encloses b. And then for encloses at the cuboid level, at the three-dimensional level, we're just going to return basically this logic, but we're going to call range encloses instead. Okay. So if to remove encloses C, that means that C was previously on. To remove is like we're gonna turn all of those off, so we don't even need to push them. So we're just gonna continue. If C completely encloses remove, split C into multiple chunks, add those chunks to result, and then break. And then what's the next case? The final case is if C partially overlaps to remove. Split C into multiple chunks, add those chunks to res, and then continue. So really the only difference here between these two cases is that this is a little bit of an optimization, where if C completely encloses to remove, that means we know that other elements inside source don't matter. However, we are reconstructing the entire result set, so we still need to iterate over everything. So we can't ever break, right? So this will just become a continue if we can't break, which means that the sort of like C completely enclosing to remove and C partially overlapping remove are basically the same case, which is good because that's like essentially the remaining code that we need to write here. So if we get here, C either completely encloses to remove or C partially overlaps to remove. In either case, split C into multiple chunks, removing the section of to remove. So we're doing kind of like what I think we'd call like a binary operation if we were doing like a 3D modeling program, where if you take a cube or a prism and then slide it over another prism, or you're doing a subtraction operation, we'd want to take the remainder of that, which is almost going to be like a cube with a corner chuck, or a prism with a corner kind of like eaten away. We want to split that into multiple cuboids. And this is where I think maybe drawing it out might be helpful. So let's go back to our whiteboard. Okay, so what are the possibilities here? The thing I'm going to draw is... Let's just draw a prism. And this is, let's say this is part of our active set. This is already bad news. I think I've kind of ruined my foreshortening completely. Let me give this another shot. Helps to make the angles a little bit more exaggerated. And these lines along the same dimension should be parallel. I'm getting my projections correctly. It'll be something like an isomorphic projection or something like that. Okay. If there's an overlap, the way that the overlap is going to play out is we're essentially, unless there's like several different ways we could do this. Either the overlap is like along like one whole dimension, and we do a cut like this. Can I undo? Let's use a different color. Like we could overlap if like to remove is something like this, right? And what we're going to be left with is essentially just the bottom half of this cube. And I say bottom half here just because of the way that this example is going. In fact, this could actually happen along any dimension. Clean this up just a little bit. So that would be a case where we end up with only one cuboid as a result. But there are several other cases. Is there a situation where we can end up with two? Well, we could just bisect. And boy, do I not love doing this kind of thing. Well, I enjoy it, but at the same time, it feels like very finicky for an advent of code problem. Another possibility along a particular dimension is that there's actually lots of possibilities, and they're all super annoying. The one where we split it into two is going to be something like, oh, I don't know. We have like almost like a kind of like a thinner thing that comes down the middle. I need to make sure that I'm parallel here. Comes through here. And then goes up. And this goes up. And then we have I'm hoping this makes a little bit of sense. This is where we'd essentially split the cuboid, the pre-existing cuboid, into a chunk that's here and a chunk that's here. There is a scenario where you can take a corner off. And there is a scenario where we can... The worst one is kind of just like if what we're going to remove is just like poking slightly into the box. In which case, I think we need to split our original cuboid. And let me give you let me try to draw that example. I don't know how general we need to be with this. It's entirely possible that the input doesn't require us to be this general. But this is an interesting problem to think about no matter what. I'd say like the worst quote-unquote case that we could run into, or the one that's going to be like kind of annoying to deal with, is if we kind of poke in just a little chunk. Gosh, I hope this reads. If we just kind of like take a little chunk out of a pre-existing cuboid. And in this case, we probably have to subdivide into what? Up to 1, 2, 3, 4, 5 sub-cuboids. Maybe we can always subdivide into 5 and just see if any of them are completely subsumed, right? Maybe that's the easiest thing to do, is to just like chunk up the existing cuboid into ranges along each dimension. I almost like that better. That's a little bit easier to think about. All right, but what does that look like? I mean, what are we subdividing along ultimately? If we think that there can be an overlap, a potential overlap along each dimension, I think we're actually splitting up our existing cuboid into 9 parts, right? Along the x-axis, there's a range that doesn't overlap with the to remove. There's a range that does overlap with it. And then there's another range on the other side that doesn't overlap. And then we have to account for that on every single axis. So if I were to draw that out, oops, this is the wrong color. So if I were to color code this, there's this range along the x-axis, this range along the y-axis, and this range along the z-axis. These are the potential subdivisions along each axis. And anything that's yellow doesn't overlap with to remove. Anything that's green does overlap with to remove. And anything that's purple doesn't overlap with to remove. And that's along each axis. And so what that in turn gives us is just lines of subdivision here. Right? So it's not nine chunks. It's actually 27 chunks. Ugh, I really feel like I'm kind of like missing something crucial here, because this is pretty ugly. Because if we get 27 chunks, we don't want to just like push all 27 of those back onto the into the active list. That'll just get really big really quickly. Oh, can we scroll to the bottom? Yes. Sorry, Crazy Wolf. Good call. I'm talking about this thing here. If it's 27 chunks, some of them are going to be contiguous with each other, so we'd have to merge them back again. This is going to be really, really gnarly. I really feel like I'm just missing something kind of crucial, because like this analysis is, I think, correct. I think the general like skeleton of this is correct. It's just that the devil is in how we do the splitting, right? And either there's something about the input that makes the splitting easier, but I'm not sure if that's the case. Now it is 27. It's 27 different chunks in the case where the existing active area completely encloses what we're supposed to remove, which is the green thing here. And that's a case where we might just need to bite the bullet and just split this into basically, it would become 26 little pieces. But there are cases, again, that I outlined up here where that's not the case. Actually, the subdivision is actually a lot, or the overlapping is a lot cleaner. So maybe what we can do is we can write a function that basically returns the non-overlapping ranges and overlapping ranges in each dimension. And that will tell us how many times we need to subdivide. So what we're talking about is essentially the difference between two cuboids, right? If we kind of like say like fn difference, what this is going to return is a vector of cuboids. And what we do here is if we get down here, we just say result.append the difference would be c.difference to remove. And this needs to be a mutable reference just because that's the way append works, which is fine. Okay, so that's not, I mean, like at least within the structure of this I think this mostly makes sense. Once again, just to back up and zoom out a little bit, if we get to an instruction that where we need to remove this volume from our set of volumes that already that are already active, we iterate over all those active ones, and we're actually accumulating a completely new list that we're going to return. If there's no overlap between them, that means that what was previously active will continue to be active, so we just push that onto our result list and continue. If what we're trying to remove completely encloses the thing that was active before, that means we just get rid of what was there before and we continue. We don't add it. In other words, we don't add that back into our result list. Otherwise, we need to do kind of like a split difference here, which is what this is about. And then we return that. Is there sort of like high level logic that we can do for adding? Well, when we add, we're gonna basically keep the original thing and then add this one, but we want to remove the difference between the two of them, right? And so we need to know what so what does removing the difference mean? Because here we're adding the difference, right? We're appending the difference. I think what we do is we keep the larger of source and to add. Well, first of all, I think there's like maybe some of this same logic that we can copy over, right? It's not going to look exactly the same, but let's pop it in there. Okay, if there is no overlap between what we're trying to add then we add, well, do we add to begin with, right? Do we just add this? As a first step. If there's no overlap, we just continue. If to add encloses what's already in there, well, to add already got added to the result, so we're just going to carry on. Otherwise, what we need to do is this actually seems pretty similar, right? We already added the area covered by what the instruction is talking about. And now we're trying to decide what to do with stuff that was already in the list. If it didn't overlap with what we added, we just add that back in. That doesn't change it. If what we added completely encloses what was already in there, we don't need to worry about what was already in there, right? This is a nice case here because it simplifies our list. Otherwise, what we need to add is anything that was part of what was already in there minus the stuff that already got added, right? It's interesting to me that these are like basically exactly the same code, whether it's remove. I feel like maybe I screwed this code up. If we're removing a volume, oh, well, I guess the difference is that the initial condition is different, right? When we're adding, we just add this as something. Okay, so maybe this makes sense, actually. We can think of adding as basically saying we're going to remove what we're about to add and then add the thing that we're going to add back in, right? That's basically what we're talking about. So we could actually implement add volume in terms of remove, where we'd say let result equal mute result equals remove volume source to add, and then the result we're gonna just add this back on at the end, and that's our implementation of adding a volume to the list, or adding a cuboid to the list. Gosh, I need to make sure that my terminology is consistent. So this is going to be add cuboid. It's going to be remove cuboid. All right, so I think this logic is roughly there. This logic is roughly there. So really the only thing that's left is like dealing with this horrible thing, which is the difference. Okay, so maybe I'm gonna write a little function that that splits ranges into overlapping chunks. So let's just call this like fn split overlaps, and the input is going to be this thing here, and the result is going to be a complicated thing. We're going to have the non-overlapping range, which is actually a vector of these ranges. Actually, it can be either 1 or 2, which is a little bit unfortunate. I don't know how to express that exactly. And then the overlap is an option, or it's a vector that can have at most one thing in it of a similar range. Bear with me here. There might be a better representation of this, but I just want to get the idea down in code, and then we can kind of continue from there. By the way, Crazy Wolf, if you're still around, it's nice to see you in chat. Thank you for stopping by and watching me tear my hair out for this problem. It really helped for me to have a picture of my overlapping cases, right? And I drew it out in text before, but why don't I just draw it out on the actual whiteboard, because we have it now. It's a little bit easier to kind of like work with. We can kind of enumerate all of our cases. Oops. So our cases for overlaps along a single dimension, they look like this. And A is going to be on top, B is going to be on the bottom. So we have this case, Let me actually use two different colors for A and B because that's a little bit easier to understand. A is going to be red. B is going to be blue. There's that case. There's the kind of mirror image of that. No, the mirror image is going to be that and that. Crazy Wolf says, I'm out the whole day. My idea was also to split the cube into new cubes, which do not overlap anymore, but split the function. But the split function breaks my head. Okay, so you and I are, I think, we're on the same plane of existence right now. So it's misery loves company. It's nice to have solidarity. Thanks for being along the ride. My head is currently breaking, and you're watching me break it on Twitch. Then we have a case where red is completely subsumed by blue. We have a case where red completely subsumes blue. And then we have a couple of cases where they're just totally disjoint from each other, right? The first one looks like this. And the second one looks like this. I don't know how legible that is, but I'm going to just maybe just draw some dotted lines between these. How do I do that using this tool? Oh gosh, that's way too dark. Let's see. And the grid actually is kind of getting in my way. Is there a way I can disable the grid view? This is a very complicated program with lots of little buttons and widgets. Background grid. Well, it's not checked. Let's do none. Okay, that's maybe a little bit easier to read. Let me actually label these. Maybe actually not, rather than having these kind of separators, I'll just label them, and that'll be a little bit easier to follow. So this is case 1, that's case 2, case 3, case 4, case 5, and case 6. Okay, so case 1 is an example. Let me try and do my window arrangement here if I can remember what the hotkeys are. I'm in a state of mind where I don't remember what my hotkeys are, so it's okay. I'm just going to manually rearrange these windows. So in this sort of like range split function, the non-overlapping pieces here are, in this case 1, is basically this chunk of the red line to the left of the blue line, and then the chunk of the blue line that's to the right of the red line. And then the overlapping range is the one in the center here, right, where we have both red and blue. The analysis for case 2 is similar. For case 3, I believe we have all overlap. I don't know if we need to account for this negative space here. That's actually something we might need to think about. I actually do wonder, in fact, if we can call non-overlap this section outside here, these two sections outside of the red section, and then the overlap just where they... I think that's probably a more correct way of approaching that. It may matter whether we're talking about the overlap on... Maybe what we can do is actually call this a non-overlap. I think this is a better way of describing it. This is an option. It might exist. And B non-overlap. Yeah, this is actually a much better way of capturing what this range split is talking about. because we can basically say this is the piece of A that doesn't overlap with B. This is the piece of B that doesn't overlap with A, and this is the piece that they all overlap with, right? And I think that will be consequential when we actually try to use this in doing our split. Now, in the case of something that's completely disjoint, A non-overlap is just going to be all of A, and then B non-overlap is going to be all of B, right? So let's just bang out this code and see what we can do with it. In fact, actually, before we even bang out that code, let's actually talk about what we're going to do with this. Okay, we have the split overlaps function, and I'm sort of proposing to you that we'll use it in this difference function somehow. And so what we're going to do is we are actually going to do overlaps on every dimension. So let Z overlap. How do I want it? Z overlap Z, OLAP Z. I don't like the word OLAP because it reminds me of databases. Let's just do overlap Z. Let's just write the full word out. Equals, I don't know why I started with Z. Let's do X. That's the conventional letter to start with when we're talking about axes. Split overlaps A.X, B.X. And I probably need to dereference these. Oh, it's self.x and other.x. I'm sorry. And then this is just, we're just going to have a version of this for Y and Z. And if there's any so the difference, so the difference that the stuff that's in common is going to be the chunk that is overlapping on all axes, right? That's going to be one cuboid. And I would say if you're taking two cuboids and you're doing differences between them, the overlap between them is always going to be a cuboid. You're never going to have like a weird shape where it's like a cuboid with another cuboid kind of hanging off of it. The overlap between those two is always going to be one cuboid. And so all you really care about is finding what is left over from the first cuboid when you remove that other chunk. And so I think what we're talking about is really just the product of all of like if so here we're actually insisting that there is going to be an overlap because we've already that there's always going to be some overlap chunk, right? This overlap should actually not be an option because we're actually we're actually asserting that this is the case. So I'm actually going to remove this as an optional case. And we should just like panic or something like that. You know what? Let's just it's too hard to think of like it's too hard to make a non-general version of this. So I'm just gonna forget that idea. So what are we actually gonna do with this? I think actually, come to think of it, these actually need to be vectors, right? Because the in example 3 and example 4, you actually have two pieces of like let's take example 4. You actually have two pieces of range A that are not overlapping with B. And similarly with variant 3 here, or example 3, there are two pieces of range B that are not overlapping with range A. Okay, now assuming that works, what we're going to do is we're going to do like the product of all of the non-overlapping areas of X, all of the non-overlapping areas of Y, and all of the non-overlapping areas of Z, and create a series of cuboids out of those, right? Here's a question. If there is no non-overlapping sections on a full dimension, how do we deal with that? And that would be the case if you are fully enclosed. That would be case 3, right? That would be the thing that we're trying to remove fully encloses a thing that already is active on one dimension. So how do we deal with that case? And what that would look like, I think, is maybe this case here, where we actually in this case we fully enclose the thing that we're trying to subdivide along the x-axis, this axis here, and also we fully enclose it along the z-axis. And so what's going to be left over, so let's just, if we run this split overlaps here in this example here, the difference is going to be, it's the difference between this blue cube and this red cube. It's a little unfortunate that I reversed the coloring here, because I said down in these examples I said A is red and B is blue, but in this case A is going to be blue and B is going to be red, right? We're subtracting this red one away from the blue one. If we do the split overlaps along the x-axis, right, that's this axis here, left to right, it's going to return a fully overlapping chunk on the x-axis for A. That's just a fully overlapping chunk. And then for B, for the non-overlapping, A non-overlap is going to be empty, because the piece of A that overlaps with the piece of B is just the entire piece of A rather. And then for B non-overlap, that chunk of the return value, it's going to return this little piece that's hanging off the left here and this little piece that's hanging off the right here. So I'm trying to figure out, okay, so I've done this along every single dimension, right? That's what we're doing here. How do we use this to kind of reconstruct a volume? Do we need to do this case by case? Is it going to be that gross, or is there something general that we can do? So if none of these have any non-overlap, if there's basically all overlap, if A overlap is empty for all of these three, that means that it is completely enclosed. That's the case where we have encloses, right? Although we probably need to we probably do need to deal with it by actually returning an empty vector here, right? If there are overlaps, if A overlap has content on every single axis, then it's going to be some version of this thing here, where actually the thing that we're subtracting out is actually enclosed by, basically B is enclosed by A. And that is the gnarliest case, because it's essentially going to have us produce maybe 26 little chunks. So, okay, what we're going back to is how do we combine these things together now that we split it along each dimension? Is this a useful representation? So let's think about that. So I think anytime you have a non-overlap that comes out of one of these, you need to make a cuboid with every other range. So with basically, okay, let's just say we have a non-overlap on. Let's just take this example again. Where we have where we have some non-overlaps is on the y-axis, right? So this is going to emit some range that is non-overlapping here. So we're going to take that, and then we're going to add a cuboid that has all of cuboid A's z dimension and all of cuboid A's x dimension. That is not the case here, right? So if we have a non-overlap, well, it is, right? So in this case, we got a non-overlap on, let's say we have a non-overlap in this case on the z-axis, right? For shape A. Shape A is the blue one. We're going to take the first non-overlapping chunk, and we're going to create a cuboid that has all of shape A's x-axis, y-axis here, and all of shape A's x-axis. And then we have this other non-overlapping chunk here, and it's going to have all of the other two axes, basically. Now let's talk about this horrible case. We have a non-overlap on the z-axis, so we're going to add everything on the x-axis and y-axis here. That's one chunk. We have a non-overlap on this other chunk on the z-axis, so we're going to add everything there. So far, so good. But then we have like what's going to be like three other cuboids, one on the side of this penetration, one on the bottom of this penetration, and one on the left side of this penetration that we need to account for. And so that's the piece that's a little bit confusing. So in that case, what we have is the overlap. We have maybe we can talk about the y-axis where we have some non-overlap basically below where this penetration occurs. And it is true that we should add on the cuboid that already has, like, it basically has the entire x and y range, or sorry, the x and z range. But the problem is it might overlap with stuff that we already accounted for. And this is a problem that is like easy for a human to do visually, but we need to be able to describe this in code. And why is it easy for a human to do? Well, a human can basically visually see where the overlaps are, right? We can kind of just like recognize those right away. And the problem is there are just like many different ways that we can combine this. We just need to pick one where the resulting set of cuboids is disjoint. And it's so funny. My brain can just like look at this and compute that almost immediately. Like if you just asked me to draw it, I'd have a hard time visualizing it, but I have a pretty good idea and I could count them. So I think it's a matter of, is there a way for me to just describe what my brain is doing there? And I worry a little bit that it's going to be a bunch of finicky ifs and elses based on whether there's an overlap on one dimension, but no overlap on the other two dimensions, or if there's like, do I need to actually split this into like a billion different subcases depending on the way that this penetration is oriented, so on and so forth? That sounds horrible, right? We could Google it, right? We could Google like, how do you do the difference between two cuboids, or really just how do you do the difference between two axis-aligned bounding boxes, right? Split those into like a set of disjoint axis-aligned bounding boxes, and we could Google that. There's probably an answer out there. I kind of want to have a think on it before I resort to Googling it, though. The name of the game here is to try to try to come up with the solution from first principle. Well, one thing we could do is we could apply that principle that I said before. So basically, anytime there's a non-overlap, so range split has a non-overlap, which is basically the piece of self here that is not overlapping with other. We could basically take the non-overlap along one dimension, and we could actually have two overlapping chunks, two non-overlapping chunks. So for each one of those, we can create a cuboid that spans the other two dimensions. So if it's for x, it would be self.y and self.z, right? Those would be the other two spans. You create cuboids like that, and then we could create a bunch of cuboids, and we'll do that for each dimension. And we'll stick that into a list, and we just need to make sure that all of those cuboids are pairwise disjoint from each other. And if they're not, we'll just have to do differences. So this could be a kind of like recursive algorithm. Boy, when I look at this, recursion is not the thing that jumps to mind, but maybe that's what we can do. So let's maybe try and play with that idea. It's a vector. I'm going to get this tablet out of the way so I can type effectively. So for each range in overlap x dot a non-overlap, we're going to push a cuboid whose x range is R and whose y range is self.y and whose z range is self.z. Oh, this is just complaining about a return value. I'm just going to return res here. And we can just do this on every single axis. It's going to be a little bit repetitive, but it's okay. We can sustain a tiny bit of repetition. This is going to be self.x, and this is going to be R. And this is going to be overlap z, self.y, and this is R. And the problem that I mentioned to you before is now actually some of these are overlapping with each other, right? So this is like a non-unique set, and we need to actually reduce that into a unique set. So let's make even another function in here. What do I want to call it? Unique. I just want to basically just like remove redundancies, right? And this may involve some splitting. So this is going to be a source, and it's going to be a vector of cuboids. And it's going to return a vector of cuboids. And in fact, we can actually fully consume the old one. So we want to do a pairwise comparison between the two. Between every single cuboid in here, and where there are overlaps with each other, we want to split one into two. Oh gosh, this is going to be ugly. For I in 0 to source.len minus 1. I don't know if these parentheses are necessary. For j in I plus 1 to source.len. It's your typical way of doing, pairwise comparisons. Let's create a result vector. If you're not able to follow along right now, I apologize. I'm not even able to follow along with what I'm doing right now, so I'm just kind of throwing stuff at a wall and seeing what sticks. We're doing some pairwise comparisons here. If there's any kind of overlap between these two, we need to actually split one of those source I dot overlap source j. Well, first of all, if there's no overlap, we can just continue. Gosh, what are we actually doing here? Because we need to know if we split the overlap and we just add them back on there still might be redundant stuff. So we may need to actually just call this again until it doesn't have any redundancies. I think this for loop may need to be in another loop. What if we just tried to find one overlap, shave off the overlap that we don't care about, and then just call this function again, make it recursive? This is a lot of code that could potentially either contain a subtle programming bug or a larger but equally subtle structural bug. It's a structural bug if my analysis is wrong, right? So this all makes me nervous. I could be writing unit tests here, but we'll get to that. We'll get to that if I need to start doing exhaustive unit testing. One reason why I don't like unit tests is that they're just hard for me to set up, and I'm lazy. If there's no overlap, then are we just adding I onto this? What we could do is just iterate through all of the source vectors, source cuboids. But we do need to be able to compare with the other ones. So this does need to be like an iterator that we're enumerating over. Index cuboid. And then what we'll do is we'll iterate over every other cuboid. And what we're trying to do is we're trying to find an overlap. If C dot overlaps with source J, then we want to take the difference between, we only want to keep the difference between C and I. So basically result dot append C dot difference source J. I guess what we could do is we could do other here, and this could be other in the slice of source that is I plus 1 in the remainder. Is that going to work too? Okay, cool. And so we don't have J anymore, so this is just other. Wonder why it's not giving me a type checking error. Did this really type check, right? What if I just add an ampersand here? Is it gonna complain? Yeah, I feel like right now the type checker doesn't know what to do with this function. It's confused. So I'm gonna reload the editor, see if that'll jostle it. One thing I can do to split up this reload process is just open this one directory. Right now I have my whole repository open, so it has a bunch of smaller Rust projects that it's analyzing. For no reason. I'm just burning CPU. Just burning down the rainforests. Okay, so let me try removing this ampersand. Will it complain? It does complain. Okay, so this all does type check. Okay, so we can append this because we know that one of these volumes overlaps with another one. The problem with this is that we don't know man. I feel like in trying to solve this split problem, I've just come back into the split problem again. And so I think my brain is about 2 or 3 levels deep, with some maybe zigs and zags along the way. And so I'm not able to think about this super clearly. Yesterday, what happened when I was working on the problem was that I had this intuition that it was going to be like a recursion problem, but it didn't hit me right away. And eventually I was just kind of like, okay, I can't really do this right now. I need to eat dinner or whatever. So I pulled away from the computer. I even said like, oh, maybe I can get Dominic to help me work on this because we do our game stream on Wednesday nights, which is tonight, and maybe we can work on problem 21 together. But I am almost interested in pulling that ripcord tonight with this problem, just because I feel like I'm talking myself into a corner on how to actually do this stuff. I actually think, like, philosophically, I'm kind of I'm kind of correct here. So let me just flesh out this difference function. What we're doing here, this like range split function is this split overlaps function is a little bit complicated, but basically what we're saying is like, what are the ranges on the x-axis for a cuboid that is already active in our list of active volumes? On the x-axis, if we have another thing that's like returning off, we just want to find areas along the x-axis that don't overlap with that area, that region that we're turning off. And then we're going to do that along the y-axis, and we're going to do that along the z-axis. And then for each of those non-overlaps on each of those axes, we are going to just add a cuboid that represents the non-overlapping chunk on that axis with basically the full size of the original cuboid. We're going to do that on each of those axes. But the problem with that is that these are going to be kind of mutually overlapping, and we need to reduce that down. So what we can do is this is actually going to be like something like remove redundant of res, right? I think it's self remove redundant. Yeah. We're just going to call this essentially like static function here. This remains to be implemented. Let's actually comment this out and call this a to-do. And then this split overlaps also needs to return some kind of range split. And for now, we're going to return none vec new and vec new. I actually feel like this one is going to be easy to write. So maybe before I take a break here and go get lunch, we can actually go ahead and just like write this function. So if a.0 is less than b.0, let's just make a mutable answer here. Let mute result equals this, and then we're going to return that result here. If a.0 is less than b.0, so if the a minimum is less than the b minimum, then our overlap is going to be result.a non-overlap.push, and we're going to push the range a.0 b.0 minus 1, right? And we can do the same thing with a's and b's reversed. If a.1 is greater than b.1, then we're also going to push the range b.1 plus 1 to a.0. a.1, sorry. We're going to copy this and flip the b's and a's. So if b.1 is greater than a.1, the b non-overlap is going to be a.1 plus 1 to b.1. Okay, so we've taken care of a non-overlap and b non-overlap. So now we need to take care of the actual overlap range. And the overlap range, we might just want to call this if range overlap function again, just so if range overlap AB, then the res.overlap equals a positive option result. And it's going to be the, I think the maximum of the minimums. A.0.max, B.0, and the minimum of the maximums. A.1.min, B.1. Is that correct? Let's take a look at our chart here. Where there's an overlap here, the lower bound is the maximum of the minimums, and the upper bound is the minimum of the maximum. So that's true in example 1. In example 2, the maximum of the minimums is going to be this edge here, and the minimum of the maximum is going to be this edge here. So that's true for example 2. What about the fully enclosing example? The overlap is going to be the maximum of the minimums, so that's this one here, and then the minimum of the maximums. That's true there. Got the maximum of the minimums. Yes, that's this one here, and then the minimum of the maximums. Yes, that's there. And because there's no overlap here, we're not going to even account for that. The reason why min and max is nice when you have a and b is it basically doesn't care about the ordering of a and b at this point. Min and max are functions that basically eliminate ordering as a consideration. So, okay, we've now implemented split overlaps. I think we can probably test that out, but I think that's pretty good. And so what remains is just this remove redundancy function, which I think might be recursive with difference, because difference also does remove redundant in it. And so I would love to go and get some lunch, so I'm going to basically hop off stream now. And if I've got the mental bandwidth, I might just hop back on if something occurs to me over lunch. Or maybe I'll just play with a piece of paper and sketch on it before I hop back on stream. I know it's fun to see my entire thought process here, but then I also start to get nervous because I'm like, oh God, I'm not making any progress, and there are people watching me. But yeah, so I'm gonna pause the stream for now, or not even just pause it. I'm gonna just like stop it for now, and then maybe hop back on. Either way, at 5 p.m. Pacific, we're gonna do our regular game dev stream. Dom and I are going to be talking about our favorite games of 2021. All right. Take it easy, everybody. We'll catch you in a little while, either talking about games or talking about this problem.
5 minutes later.
Do you want to help me out with
fun.
an advent of code problem?
Dude, bring it on. I'm excited. I want to see how bad this got.
So this is the second day in a row where I have worked on a problem for 2 hours.
Uh-oh.
And I kind of was like, God, I'm on stream right now. People are watching me do this, and I'm feeling self-conscious about churning on this thing.
So it sounds like we're gonna knock it out then, is what you're telling me. Is this 2022 or 21?
This is 21. But then like a couple hours later, for yesterday's problem, I was like, okay, I'm gonna just eat some dinner. And then as I was like, as these things go in software engineering, I was like, oh, I know how to solve it. Do you know what I mean? Like, it's just like,
absolutely.
just step away and then you kind of figure it out. And then like I banged it out in the next 20 minutes.
There's a better word for shower thoughts, and I don't know what it is, but it's shower thoughts.
Well, I think there's probably some like Malcolm Gladwell blink/tipping point kind of book about the kind of like right brain function in the unconscious mind, where, you know, like you sleep on something, you chew on it for a little while, and then suddenly it comes to you, right? There's probably like some pop science book out there about that particular.
I kind of think of it. I think of it as like sending it to the cloud. Like you're kind of like machine learning it for a
sending
couple
it
hours.
To the butt.
Send it to the butt. Yeah, it's like you go send it off to like a nonsense machine learning algorithm and let it sort of just churn in the background for a couple hours, and then like if you give that enough time, sometimes it like spits an answer out for you.
Yeah.
But like it's unpredictable.
So actually, this is the second problem in a row where I actually literally said on stream as I was working on it the first session, I was like, you know what, I'm just going to step away from this, and maybe if there's time, I'll do it with Dominic, and having two heads is going to be better than one. Yesterday's, I didn't get that far because I was able to figure it out.
Nice.
Today's was the same way, but I think I might have a sort of an idea on how to do it, but let me talk you through it.
Okay, great.
I'm not going to read the whole description. I'm just going to give you some sense of how to do it. And in fact, let me actually get my iPad real quick, because I think drawing some of these pictures will help.
Okay. And I've got this on my screen too. So operating as extreme motion depths, overload the reactor. The reactor is a large three-dimensional grid made up entirely of cubes, one cube per integer three-dimensional coordinate x,
It's made
y,
of
z.
cubes, I tell you. It's made of cubes.
Okay,
Sorry, that's
so
a Soylent Green joke. I don't know.
yes. So Soylent cubes are made of people. So it's a three-dimensional shape
It's a voxel field. Think of it that
It's a
way.
right. It's a voxel field, and all it's trying to tell us is that every voxel is either on or off.
Yes.
Okay.
It's either on or off.
It's a binary voxel field.
Yeah. And you basically have these instructions that give you what they're calling a cuboid. You can also think of as just an axis-aligned bounding box or prism in this voxel field. And it's inclusive of the bounds. And if it's prefixed with the word on, it means to basically populate those everything inside of that prism in the voxel field. And if it's off, you flip them off.
Okay.
And so what you can imagine this doing is like some of these instructions cover really, really huge fields or really, really huge volumes. Other times they cover really, really small ones. And both the first part of the problem, the second part of the problem are about counting the number of voxels that are on after you've processed all of the instructions. Now, if you look at the input, some of the volumes start to get super massive, like tens of thousands of units on each dimension.
Shit. Okay.
Right?
And wait, did you solve part one yet?
Yeah, so I solved part one. The thing with part one is they say in part one, all you need to worry about is this 100 by 100 by 100 area around the origin. And so that means you can basically filter out all of the instructions that don't overlap on any of the three axes if they don't overlap over the origin.
Gotcha.
And you can basically track a list of all of the coordinates, the three tuples that are active. So you're basically down to the granularity of one voxel where you just say, is this particular coordinate on or off? And you just run through the instructions. I think out of the input, only 20 of the like hundreds of instructions actually overlap this central area. So it's pretty easy to keep track of.
Nice.
The part two one is you have to count them all, right? And so in their example, this extremely large 64-bit positive number is the number they're on. So like you can't create a set that's this many units big, right?
Nope.
It's just not possible.
Wow.
So the algorithm I came up with it's a lot of like extra support code, which is what makes this scary to me. Let me actually move some of this code out of the way.
Wait, sorry, quick question too. When you receive an on or off instruction, it's not flipping. It's not like one of those things where you press a button and it changes to their state, but it's actually taking the entire cube and just setting the state to on or off. You don't have to track like the previous value.
You don't have to look at what was previous there and like reverse it.
Okay,
that would be a much harder problem.
I think so. Yeah. Okay, cool.
Oops. Yeah, but let me show you the input. Yeah, so there's like hundreds of instructions, right? There's actually 420. Lord. Get big.
Nice.
But again, like if you're only worried about like the 100 by 100 by 100 space around the origin, only 20 of these end up applying. But we have to count for all of them, right? So we can't keep track of our state that we're tracking instruction by instruction cannot be individual voxels, right?
Okay.
So I thought, why don't we just keep track of cuboids? So rather than a list of individual voxels, we'll have a list of disjoint cuboids. And a cuboid is this prism shape, right? And each one will have some dimensions. And then when we get one of these instructions, we'll just compare this to what's already there. And either we'll add, it's like for this on one, we'll either just like add this entire cuboid as a new entry in our list, or we like have to compare that to everything that's already in our list and make sure that we get rid of any overlap so we don't double count anything, right? Because we need an accurate count by the end.
So are you saying that like if we have an existing cuboid, we get a new one and it intersects, we're actually splitting the old cuboid into a smaller shape, and the chunk that was in the old cuboid is gone because now it's been flipped by this one. So we do it in order, top to bottom,
Yep, you hit it
and
on the
just
head.
split as we go down. That
You hit
makes
it
a
on the
lot of
head.
sense.
And
Yeah.
then removing it is sort of a similar idea, but when you want to remove it, you basically like if you get an off instruction, you just have to compare this cuboid, or I'm using the term cuboid. That's what I mean by this kind of axis aligned
Yeah. Yeah.
set
Yeah.
of voxels. You basically compare that cuboid to everything that's already there. If
Mhm.
this cuboid fully encloses a cuboid that's already in the list, you just get rid of that one. The trick is if it kind of intersects but is not fully enclosed by it, what do you do there? You kind of have to split it up into like sub cuboids, right?
Mhm.
So I think that algorithm is pretty easy to visualize. The devil is in the splitting.
Yep. What is the worst case runtime of that split for 420? It's not 420 factorial.
Are you talking for any one of these things?
I guess I'm thinking for the algorithm itself. Like, I think
Yeah.
Sorry, I think it's fine. I'm kind of just curious what the runtime is because
Yeah. So there's a lot of subtlety in how you split. Like I think maybe what you're saying is like, how much worse do you make? How much worse do you make the set of active cuboids if you're doing splitting, right? Like,
yeah,
because you could potentially split one, and like, I think the most, if you were doing this like super naively, which maybe we have to do, the most you can split a pre-existing cuboid into is like 27 other cuboids. Basically, think of it as like a if you separate on each dimension in each dimension into 3 chunks, that'll give you like a 3x3x3 Rubik's cube, if you think about it that way. And that has 27 elements in it.
Okay. Yeah, that's the worst case then. Great.
Yeah. Okay.
I think this is still space efficient compared to trying to do a multi-trillion element array or whatever it turns out to be.
I don't know how many. Actually, this is a fun exercise to determine like exactly how big this number is. So let's add some commas. Commas are your friends. In classical Chinese, which also means classical Korean and Japanese, the commas go after every 4 digits. It's a real head fuck. Yeah. They don't really use commas. They didn't have the same notion of Arabic digits and that kind of thing, but basically like they make a new word every 4 digits rather than every 3.
Gotcha.
Yeah. This is millions, this is billions, this is 2 quadrillion. Nice.
And that's 2 quadrillion on, so probably like double that. Yeah, I don't think we have the bits for that.
Yeah. And you have to iterate all this shit to turn it on and off too. It'd be slow.
I hope someone wrote the brute force algorithm today, but it's probably still running. I assume that problem is like such that you can't run it in a day on normal hardware or something.
I don't think you could fit it in memory. You could like map reduce it, like have it on disk across a bunch of different, like in a giant compute cluster, and then I mean, I don't know. Do you have a data warehouse at work that you can search across?
We probably do.
I look at some of the stats because like we had a data warehouse it was like the craziest. It was like the best thing that we had in engineering. It was like we could just query so much of our data in our logs and that kind of thing. But I would like run these like really complicated queries, and it's just like, oh, we just processed 100 gigabytes of data for you, and I'm like, what the hell? Okay, so the actual sort of like outline of this, this is the first advent of code problem that I've actually kind of like had a little bit of discipline and kind of chunked up into sub problems because I couldn't figure it out. I couldn't keep the whole thing in my head. So it is chunked up. So we parse the instructions. That was really, really straightforward. Then we have a list of cuboids that are active. Okay. And then for each, go ahead.
Oh, because everything is off. An off instruction only is subtract from a current cuboid. Exactly. Otherwise it's nothing. Great.
Exactly. So for each one of those instructions, we're actually replacing, I have these 2 functions, add cuboid and remove cuboid. They each take the current set of cuboids and they take the current instruction that you're iterating over, and they will return the full new set of cuboids afterwards. So you can see that this active vector is being replaced every iteration of this loop.
Okay.
Let's talk about remove cuboid first, because I actually implemented add cuboid in terms of remove cuboid. I say implemented in scare quotes because I haven't actually run this yet.
Oh, interesting. So to add, you basically you're negating, you're running remove for that space
And then adding that to the end. Yeah.
and adding it to the end. That's really clever. So you're gonna fracture stuff, but you've got a set of only adds. I love it.
Yeah. Okay, yeah. So you read this code is really easy to basically parse at a glance. But yeah, the idea is that this will get rid of any kind of overlap with the thing that we're adding, and then we're going to add this here.
Right. Cool.
So to remove a cuboid, we're going to create a new vector that's going to be our eventual new set of everything, right? And that's what we return at the end of this. And then what we do is we iterate over every cuboid that we currently have. And then what we say is, if there's no overlap between the thing that we're subtracting off of everything and the current cuboid that we're processing, that means that these two have no relevance to each other. I can just add the pre-existing cuboid back into the list and then keep going, right? If the thing that we're subtracting off the current set actually fully encloses a pre-existing cuboid, I can just ignore that pre-existing cuboid and
it's gone.
Going,
yeah.
Right.
Yep.
The trick is, if we've gotten down here, either completely encloses to remove, so it's the reverse relationship to this, or C partially overlaps to remove. I don't know why I made this distinction. There's just some overlap that we have to care about, right? In either case, what we're going to do is we're going to split C into multiple chunks, removing the overlap between.
Cool. Yeah. This is a very clever little like funky set intersection problem.
Yes, that's exactly right. It's a shape intersection problem. So the devil is in how you do this thing, right? So I sort of like mapped out a bunch of different ways that you can have a difference, and I'll try my best to redraw these here.
Well, I think to your point, you're basically creating a Rubik's Cube with the center missing every time.
There's a lot of different variations. So let's say the blue one is one that's already on, and then we're subtracting.
Hope you brought your perspective drawing skills tonight.
Yeah. One way that we could subtract is if we had total enclosure over two of the axes.
Yep.
And here, the stuff that you would keep is basically just the bottom half of this, right? Another potential case, and there's lots of potential cases.
Jeff, just in seeing this so far, I feel like is there sort of a naive solution where you always slice it into 27, but a lot of those are 0 slices, and then you just don't add them?
Yeah, I actually was gonna try to do that.
Cool.
Yeah, that was the sort of solution that I wanted to pursue. I thought of one that might be better than that, but
cool. All right.
We can take a look at that in a second.
Sweet. Yeah, I only say that because it seems like I'm trying to figure out if that applies to everything easily or not.
Yeah, let me give you a gnarly one. So, whoops. So a gnarly one might be like, gosh, I'm not even sure if I know how to draw this.
No, I'm picking up what you're putting down. It goes through and out the top.
Yeah. So you kind of like you make like a U shape out of this.
Yeah, you're turning the cuboid into a taco.
Yeah. There's also the one that you thought of before, which is that actually the one that currently pre-exists fully encloses the thing we're trying to remove. So it's like totally encased in here. Right? And so on and so forth. There's one where you just kind of penetrate like a screwdriver or a nail, right? There's that version as well. And then there's the classic corner to corner, right? Like corners overlapping corners. So I kind of like crunched on this for a while. I thought, okay, well, how did I actually start doing this? So I started writing this like difference function. And I wrote this function that I called split overlaps. I do this on every single dimension. What split overlaps does, I'm taking a look at the is it basically tells you along that axis, what is the range along the axis of the actual overlap? And then for the first segment that you passed in, what are the ranges that don't overlap? And I can draw out the cases for you, right?
Okay. Interesting.
So here's one overlap example.
Do you want to put the iPad back on the screen?
Oh, yes.
Lost them.
I'm sorry.
That's okay.
Here's one overlap example, right? This is all in one dimension.
Oh, interesting. So you can do the entire set of.
Here's another overlap example.
I like it. So like the actual enumeration of overlapping on each axis is actually a much smaller problem.
Yeah, the problem I ran into though, right? You can see how there's just like different variations of overlapping, right? And there's also different variations of disjoint. The problem I ran into is that, okay, so you do that on every axis. And I thought, okay, well, if there's like a non-overlapping piece on one axis, that means I can create a new cuboid that uses a non-overlapping range on that axis. Okay. And literally the entire Y and Z part of the rest of that cuboid is valid, right? It should, because like where Y and Z equal the original are the same as the original cuboid, in this range on X, it doesn't overlap with the thing you're trying to remove at all. So this cuboid will definitely be remaining, right?
That seems right. Yep.
And then I did that on against every axis.
Okay.
The problem with that is these all overlap with each other, right? If you're only looking at one axis at a time, they all overlap with each other. So I was like,
Beautiful.
Okay, maybe I can just like remove the redundant, somehow like filter out the redundancies. And then when I started writing this, I was like, oh, maybe I need to actually call difference to filter out the redundancies.
Oh no.
So these two were like recursive against each other. And then I was like, okay, this is more complicated than I wanted it to be.
Cool.
So you kind of get you have the problem sort of in your head, right? Okay. So I thought of a different way of doing the difference.
Okay.
So the idea that I had, sorry, go ahead.
Is it different than what I just suggested?
Splitting it into 27 chunks. It is a little bit different. Yeah.
I guess sort of doing the like, it's like plus it's basically 3 directions on each axis.
We can do that, but that would have to be special cased because we don't always have 3 chunks of overlap, right? If we go back to this, the only situation where we actually have three things to worry about is this one. Whereas this one, it's a little weird.
Yeah, I guess I was thinking in doing it as 3 chunks, you could solve the edge case by having it always fall back to 0, basically. Like you generate a bunch of 0 cuboids and call them at the end.
Right.
So you could automate the process, call the 0 ones, and then see what's left over.
Right.
So
let me throw the idea that I had at you, which I'm hazarding that it's going to be simpler to think about.
Cool.
So we do something like this. But But what we would do is we would find the first non-overlapping section. We would do this. So we wouldn't do it in a for loop. We would just like take the first one in this list, push that on there, then take whatever's left and call difference recursively on this.
Okay. So rather than generating it like this, you won't generate an overlapping one because you're slicing out.
I'm basically taking one chunk off and saying,
do it
okay,
again.
that's in our list, and then I'm calling it again. Yeah.
On the new smaller volume that's been
exactly.
shrunken by what you just sliced off.
Yeah.
Cool. Yeah. And then at some point you hit 0 on one axis and you're done.
Exactly. Yeah.
I like it.
So I think that's a lot simpler to think about than like trying to subdivide it into like 27 things and thinking of all the different cases. So I think that's the way that I'm going to try to do this.
Sick.
All right. But I feel better already being able to talk out loud about it. So the way this is going to work is, I think, split overlaps. I decided that I wanted to actually express this structure a little bit differently.
Okay.
Where I'm going to just call this like the A suffix. And I'll explain what that terminology means in a second. The overlap here, actually, this isn't an option because you don't necessarily have an overlap between A and B, right? So it
Correct.
may or may not exist. And then the A overlap is basically, or the A non-overlap rather, is a vector because you could have either one or two pieces of A that aren't overlapping with B, right?
Is there ever a case where you're not overlapping on one axis?
There technically isn't, based on the way that we get to this piece of code.
Okay. Yeah.
But I wasn't sure if I wanted to make that assumption for this function specifically.
Perfect. Okay. No, just making sure that like I was sort of in the right ballpark, that shouldn't be possible here.
Yeah. So originally I structured this as a vector because like in this case, like A has only one piece that's not overlapping with B, right? It's got this chunk right here. But in this case here, it actually has two pieces that aren't overlapping with B, which is why I made it a vector. As I thought about this more, I think it's actually useful to be very explicit, whether it's the piece towards the minimal side or the piece towards the maximal size. And because you can only have two of these, the way that I'm actually expressing this is I'm calling it a suffix. I don't know if that's the right term, but it's whatever. It's like the left overhang and the right overhang, or the minimal overhang and the maximal overhang.
Okay. I like min and max there.
So min overhang or min non-overlap. This is very explicit. It's verbose, but very explicit.
No, it's good. It's good. And the same thing for B. Yeah.
And then what these would start off as is all just like, somehow I didn't
so you copy that.
Copy.
Yeah.
And all of these would just be none by default. What? Sorry.
That's okay.
Keyboard difficulties. I really want better keys on my keyboard. But
what are you using?
I'm using an Apple Magic Keyboard. But I've bought an Apple Magic Keyboard twice this year because that's like literally the only thing that's been working for me. I bought the non 10 key one and I bought the 10 key one. And pretty soon I'm going to buy the one with Touch ID. You know, it's just like I'm going to send Apple all of my money.
I thought about that. Yeah.
Yeah. So in this case, you can follow me in this function here. We're just basically saying, I just want to split A and B up into all these like respective chunks. If there's a range overlap between A and B, then the overlap is basically the greater of the two minimums and the lesser of the two maximums. That's the overlap there. And then this is going to be the A min overlap, actually. So it'd be A. It would actually end up looking like this.
Yep.
Right, because if A is less, if the minimum part of A is less than the minimum part of B, that means there's like a little piece of A that's like hanging out here, right? Similarly, on the maximal side, a max non-overlap. So this is, I think, like it was like, you can see I'm overwriting code over here, but like essentially I had the logic in there. There was actually just some information loss, right? Because if you push it onto a vector, you're not really sure
which side is which
side it's hanging off of.
Yep.
Yeah. And then we'll do the same thing here. Only this is B min and B max.
And B max.
Okay.
Nice.
This is not none. This is, I think I accidentally command D'd that.
Oh, too far. Yeah.
I went too far. They went too far. Okay.
Cool.
So that function I think is mostly pretty legible. I'm gonna get rid of this remove redundant. This is like when I got a step too far.
Okay.
Okay. So the way that I would like this function to go is that basically what I'm going to do is for each one of these axes, I'm going to go, do you have a min overlap? If so, I'm going to add that a min overlap along the other two dimensions, like making a cuboid out of that, stick it onto the list, and then recursively call the function with the stuff that's not part of the minimum overlap.
Yes. So maybe overly efficient, but like, can we do that after X?
No, I think you're absolutely right. So the way that this would work is we'd say if let some overlap, non-overlap, is equal to overlap X dot a min non-overlap. So if that exists,
yeah,
we have a result up here. Actually, I think the result can be in here. The result is going to be equal to a vector with a cuboid in it. And the cuboid's dimensions along the x-axis is just the non-overlap, right? And the dimensions along the y-axis is the previous.
Yep. And the z is the same.
And this is the previous z. And then what we're going to do is like, if the non-overlap if the maximum non-overlap is less than the maximum of the original dimension, that means you still have some stuff left over along that dimension, right? This is actually always going to be true, like technically when we call this function. But this is basically where I'm going to make a recursive call, right?
Okay.
We are going to push, or actually we're going to append onto the result, which is a vector of stuff. We're actually going to return append. I'm not actually sure if append does what I want. Append doesn't have a return value. This is actually a void return. So I think we have to do like return res down here, right? We are going to append the difference between those two. And we can actually do this manually, right? We're going to append to the difference. And to call difference, we're calling it on a cuboid, right? So it is, let's call this the rest. And the rest of this is actually a cuboid whose x dimension is the non-overlap. And because this is the minimum piece, we're going to take the greater side of it, add 1. And then it'll go to self.x.1, right? It'll go all the way to the end of the original one.
Yep.
And then it's the same here, right?
Yep.
So I think this computation is why it is useful to separate between the min overlap and the max overlap. right?
Absolutely. Yeah, because we're going to be taking the other direction on, yeah.
Yeah, so we can now do rest dot difference of other, right? This is the recursive call.
Nice.
And it's complaining here because this is actually supposed to be a mutable reference. So we just need to pass whatever we compute here as a mutable reference, right? That's just what this function accepts.
Cool.
All right. So we're going to write this same thing for the max overlap, right?
Mhm.
And this code is the same, but then what we're going to say here is if the minimum part of the non-overlap is greater than the minimum part of the original, is that right? This case here, this thing is just trying to account for the case where
the zero
we
case.
fully enclose, we like fully enclose the other one, right?
Yep.
So I think this is the right reversal of this thing, right?
Yeah.
Okay. And then now this is going to be different, right? This is going to be the minimum X value on this dimension, and then non-overlap dot 0 minus 1, right?
Oh, because we've taken it from, yep.
If you think
That's
about
correct.
this on the X-axis, this case up here takes off the left chunk.
Exactly.
And this case over here takes off the right chunk, right? So if we were looking at this example here, like the sort of min overlap part is the non-overlap is here, the max non-overlap is here.
Yep.
Right?
Yep. Cool.
Okay, so we could repeat this code for every single dimension.
We could,
but I'd rather write a for loop, right? What I want to iterate over is this dot
axis.
X. Yeah, is the axis. Right now I have this expressed as a tuple, or rather it's an XYZ. So it's hard to iterate over these, right?
Yes.
But Rust gives you this cool thing called the index trait. And what that is like if you have an index trait. Does Java have this?
I don't know. I don't think I've ever encountered this particular paradigm. I'm excited to see what this is about to be.
I think it's actually you have to pass it a template parameter, which is what is the value of the index, because the index could be an enum, for example, right? You could force it to be like an enum, and it returns. I think you have to declare type output equals I64, the stuff that we contain. You could just do this self.x, self.y, self.z iter. Nathaniel Bumpo, what about for iter index mute? Like, what if I wanted to mutate? I would just do iter mute in that case. I think I want to know what the index is. So Nathaniel Bumpo, thank you for the suggestion. I'm going to try to press ahead with what I'm doing right now. I know it's a lot of code, but I think this might be helpful in some cases. Oh,
interesting.
Yeah, because like when we write this,
I like their suggestion. Yeah.
When we write this, for example, we're going to want to know which of these axes to put non-overlap into, so it helps to have a number, right? Because we're going to be iterating over a for loop, right? So we're not just iterating over these values. We're also need to know the index to know what to write over. So
with an index trait, you'll be able to read and write to the property you expect to in the object.
What I want to be able to do is I want to be able to do cuboid 0, which is the x-axis.
Oh, that's sick.
And I actually want it to be a cuboid I, right? Because I'm actually iterating over 0 through 2. Yeah.
Cool.
So that's what this is doing. And what we're going to do is we're just going to match on the usize, the index. And if it's 0, return self.x. If it's 1, return self.y. If it's 2, return self.z. And if it's anything else, we just panic at the disco saying index out of range. index.
That is a very cool little pattern to have.
Yeah. And so what's going to happen is if what the compiler is doing here is like if it ever sees anything that like cuboid with this kind of construction into it, the compiler is going to go, okay, I know what type cuboid is, and I have all the type of information about cuboid. Does it implement the index trait? Or if it's a primitive, if it's like an array, I'm going to handle it a special way. But otherwise,
That's really clever.
This is essentially how they're doing operator overloading for the bracket operator, right?
Mm-hmm.
And you can do this in C++. I'm not sure about other languages, but C++ does let you overload the the array access operator.
I like it.
Yeah.
I've never seen this.
Yeah. What's a little bit more of a pain in the butt is that we also have to write index mute.
Oh, that is annoying.
Which is the mutation version of this, right? We get rid of this. This becomes index mute. There's a mutable here, mutable here, mutable.
Oh my lord.
Mutable.
Yeah, I'm not surprised by Rust doing this in particular.
Yeah. I guess this is just like, this would be like a read-only class, and this is one that also implements writing as well. So I think it's just reasonable for them to do that. In fact, these two traits are related to each other. If you look at index mute, it says your trait is index mute, where the thing that we're attaching it to also has to implement the index trait as well.
So if you commented out the top index trait, this would be just, it would have a compiler error.
Complain.
Yeah. Great.
Yeah. See, now it's
Very
it's
quickly.
complaining.
Clever.
And so this self output here is actually referring to the output type that was declared in this trait.
I love to give Rust some shit, but this is kind of just like working with immutable JS, and I like that they can enforce it instead of immutable JS, where you have to write a different language inside JavaScript to work with it.
It's very, very nice. Yeah.
That's good shit.
Okay. So I'm gonna get rid of the rest of this stuff.
Oh wait, you're about to delete the max version, aren't you? Oh no,
yes,
sorry.
I don't want to delete the max version. I want the max. Let's take it to the max.
Sweet.
Am I missing a brace somewhere?
Doesn't look like it, but it sure seems to think you are.
Nope. Good God, I deleted too much. Oh, you know what? It's just complaining I'm not returning anything. So I'm just gonna return vec new down here. Cool. This is in case we don't hit any of these two cases. But this is only the x-axis, right? This is just the x-axis. We need to do this on every single dimension because we might not have non-overlaps on the x-axis.
Yes.
And in fact,
is this 012.iter or 0 to 2? Yeah.
Yeah, I'm gonna actually call this just the overlap split.
Okay.
And then what we're going to do is we're going to go 0 to 2 we're going to do this on each axis, right?
Yep.
Okay, so anytime we see .x right here and here, we're actually doing axis, right?
That's amazing.
And then for this thing, let's actually just say let the chunk that we're keeping equal ourselves dot clone. We're just going to make a straight up copy, and then we're going to do chunk axis equals non-overlap, right?
Love it.
And then our result is just the chunk. Oh, I keep hitting enter on the wrong side. Oh, this needs to be mutable.
Here. Oh, yep. And then same thing inside of here.
Rest so Nathaniel Bumpo, this is the thing that I wanted to be able to do, and I'm not sure if iter mute is gonna get me there in a way that's super clean. That's as clean as this, despite the fact that I've got 20 lines of code here that I had to manage. Hopefully this will seem worth it. So this is our chunk. If there is an overlap, let mute rest equals, it's gonna be the same pattern here, but rest axis is equal to this piece right here, right? Does that?
He sent a link for this, how to iterate.
This is
over
how
the
you
field.
iterate over fields mutably.
Ooh. Yeah.
Iter mute. Yeah, I mean, I think this is actually what I was expecting. You would call iter mute. I guess you have to make sure that these are mutable references, which is interesting. I would have thought that these would be owned if, I guess they're not owned. If you put them in the, oh, I see. You can't move s.x in here because it's owned by s, and you don't want to drop s. So they're in here, iter mute, and then you do this thing, this sort of C-ism, which I think I kind of get. If you're used to C, which nobody should be, that would be familiar, right? But that's a great suggestion. Thank you for pointing us that way.
Yeah, that's a little simpler, less code. I think harder to read.
Yeah, and I think it would be harder to do something like this axis, because essentially we'd have to basically increment the iterator n number of times, axis number of times, right?
Oh,
in order to get what we wanted. And we could do that. I think you can do like iterator.nth, and we'll just like skip ahead that number of times that you pass in. So maybe that would be okay. This, I think, in context, is legible though, right? Did what I did here make sense also? Essentially what we're doing is we're making a copy of the original one, but given the axis that we're currently operating on, we're just replacing it with some range, either the stuff that is part of the non-overlap or the stuff that's not part of the non-overlap.
Oh, I thought that stuff was super clear. Yeah,
okay,
I mean,
cool.
We just wrote this code. Now it's more generic. I love it.
Okay.
So
this one needs the same treatment, right?
I was gonna say the chunk is exactly the same actually, which is fun.
It is, yeah.
Big fan.
Okay, and then this is where we diverge, right? It's just that this piece.
Nathaniel Bumpo says index mute is probably better if you want to actually have reusable code since it's more ergonomic. Yeah, I definitely would describe this as more ergonomic.
Yeah, I mean, in our case here, there's not like a huge concern for reusability because this is just like one program in one file. So maybe it's a toss up on what we would do here. I think my instinct right now, as of this moment, is like this sort of feels a little bit easier to work with than using a mutable iterator. But I would love to experiment with the mutable iterator pattern over a tuple. It's cool that they do that. It must be at runtime. I wonder how it knows, right? Maybe just like it just knows to section it off. Somehow it's deriving code for that iterator because it like knows how to iterate over the fields. It's something that you would have to use reflection for, like runtime reflection for in a dynamic language. Okay.
So wait a minute. So is this done? Does this work? Well, we haven't run it yet.
We haven't run it yet.
We've got the difference. Oh yeah, this was the incomplete function before. I feel pretty good about it.
Right.
Do we need to?
Are there edge cases here?
What about? Say, do we need to zero anything out? Is there like a case where what happens in the? Yeah, if you're overlapping on like 3 edges or something, or sorry, if you're exactly on 3 edges and you have 0. I don't think it gets called. I think it works fine.
Right.
I think you slice a slice off and then you go for the next slice until there's nothing, and then you return vector new and you're done.
So you slice the thing off and then you're done. And in this case handles the situation where
Jeff, there's a bunch of
right?
There's a bunch of self.x in there. It needs to be self-axis.
Oh, great call.
Nice. Better.
So it would be easy to forget about this case, this condition. And if we didn't account for this condition, you could be trying to, like, you might have a degenerate rest, right? Like rest might be, if you sort of set this up, maybe these two values are actually like the first value is not actually less than the second value, right? Like you could end up in that situation.
Yep.
And so that's what this condition is trying to guarantee.
No, I think that makes a lot of sense. Is there, what do we use bmin non-overlap and bmax non-overlap at all? Do they exist for a reason?
We don't care about B non-overlaps in this case because this is the thing that we're subtracting from, and so for this algorithm we don't care.
Yeah.
I just added them in here because I didn't know if I would need them or not, but we could trim them out if we feel like we don't want them.
Well, fair enough. Let's save it till we know we don't need them.
I actually think it makes this function in a vacuum easier to read if you handle all of the cases rather than just.
It's weird, right? Yeah, I agree.
You generally don't want to over like program or add code that you don't need, and yet at the same time, it can harm legibility if you're sort of like making assumptions about the scenarios in which a particular function is being called, right? Okay, so if we don't hit any overlaps at all on any axis, which might happen as we recurse, right? It might happen as we recurse. It won't happen the first time, right? Because the first time we get here,
we know it's true.
We'll skip over it. But as we recurse, we might get to that point. We'll just return an empty vector, right? And that empty vector will get returned up the stack, and it may even get returned here. And if you try to append that, nothing will happen. So I think this might be it, right? So should we try to run it?
Yeah. So after we do all the differencing, I guess a lot of this is done for your previous problem. Does it add up all the cubes at the end, or do we need to?
Okay. Yeah. Great question. So let's actually bring it back around, right? So the main function, we add a remove, right? That was this, and remove is where we did the differencing, right? And then we return that back up. It runs all the instructions. We're going to have a bunch of chopped up cubes inside active. And so I'm doing a reduce over that.
Cool. Oh, and you've got a volume function.
Let's just accumulate the volume here, right?
I think you should run it.
Okay.
I am optimistic, though I'm afraid to break our streak of it working perfectly the first time we run code.
That is your streak and not my streak.
Yeah. Sorry, I'm afraid of breaking my
streak.
I'm afraid of breaking my streak.
Yeah.
So let's see what we got. How long do you think this is going to take to run?
Long time to compile. Oh my God, it almost happened instantaneously. That's a really big number. I have no idea.
It's
what do you
a
think,
big
Tom?
number.
Think it's right? You think it's right? It's too low.
Too low.
Fiddlesticks. Damn. Well, we can run it on the sample input.
That's a great idea. Yeah, let's see what we got.
And yeah, so I don't know how to compare this exactly.
Put them next to each other in a file. Yeah, I'm
guessing it's going to be lower, right? Yeah, considerably lower.
Considerably. Well, damn.
Well, I guess we can take a look at the obvious things, like are we getting all the instructions, for example? And let's even just call instructions.length. Let's return here. I don't care about the rest of this. There are 60 instructions. Ooh, that seems like a problem, doesn't it?
No, there's 60 in the data that we're running.
Oh, in the data that
sample data.
Okay,
sample
yeah, so that's
60.
actually right. Right, yeah, there's exactly 60. Okay, so that's not the problem.
Since they gave us input of 420, and they couldn't make their sample data 69 lines long. I'm very disappointed in the authors of Advent of Code.
The 420 does seem quite deliberate, right? They could have chosen anything.
Maybe could be random. Maybe you got lucky today.
93,533. I'm just checking to see that the parsing is correct. I
Absolutely.
think it's fine because like the part one I did the parse is where I wrote the parsing and it was fine. So I think the parsing is okay.
And there's no more clamping of any sort going on in the code, right? It looks like that's gone.
There's no filtering of the instructions. Yeah, we're just calling parse instruction here. Parse instruction, I believe, should be doing something quite naive.
Cool.
Yeah.
Do you want to try to construct like a very naive example, like 2 instructions on off, or even on? Let's see if we come up with
yeah, let's do it.
Reasonable answers. Because we should be able to like construct our own version of this pretty easily.
Yes. Okay, so let's go ahead and ignore this. And instead, let's let instructions be a vector of instructions. And let's make it on. And the volume is going to look like this. And let's do something super naive, right?
Yep. 10. We need more than, I think I'm worried about the 1 case. Yeah.
And do you want me to vary these numbers? There's a trade-off between varying the numbers and making it easy to read, right?
Well, let's make this. This is like our unit cube, and from here we should be able to add. Like we should be able to add a cube inside it, get the same number out, which is
So let's go ahead and just run this, right?
Fair.
I'm gonna hide my Zoom controls. They keep popping up down here.
Oh.
Hide floating meeting controls.
I can't.
I don't like you. 1331. That seems wrong. That's
just wrong.
Isn't that interesting?
That's really interesting. How the fuck did it do that?
Well, let me make sure that my volume calculation is correct, right? Maybe there's just something straight up wrong. I am doing the max minus the min plus 1.
Plus.
You go from 0 to 10. Actually, 0 to 10 is 11 things, right? I think I wanted to go 0 to 9 if I wanted 1,000. Let's do that.
Oh, this is 11 times 11 times 11. That's the correct number. Yeah.
Is it? Okay. So maybe the math is correct. Oh, damn it. I hit escape. It's the death of me.
Can't do it. Beautiful.
Yeah.
Beautiful. Okay. So if we removed a 4x4 cube in the center of that, we should get 936.
4x4. So that could be anything, right? That could be 0 to 3. And that is wrong.
That's wrong.
Yeah.
Great.
That's perfect. We have a simple example.
I love it.
In fact, we could do this even, right? And this would be wrong. This is 5 by 5 by 5. What is that? 125 minus
60 minus 64 should be 61. Nope.
That is wronger than wrong.
Whoa.
Okay. So it's basically when we get to remove that we're getting to the issue, right?
Oh wait, can you do something silly for me?
Sure.
Oh, sorry. This is on true. Great. I love it.
Oh, this is untrue. Sorry.
What we should have gotten the same number out. Should have been 125.
Oh,
like
that is correct.
None of that. So can you do on false? I want to see that run too. I'm curious.
45.
Nope. Should be 61.
Okay. This is good.
Yeah. So on true is great because this shouldn't
on true. And let's actually do this like the stupidest possible thing, right? Actually, this is the dumbest thing.
Correct. 124 or bust. Okay. Do you want to do on false? I feel like we are having the experience of remove
being the problem.
Yeah.
Yeah. So it should be 124 for sure. Right?
Yep.
Okay. So we add the cuboid. And really what we can do is even like, we can print out what the result is every single iteration, right?
Oh, I love it. Yeah. Oh, interesting. I wonder how that add works in the first removal case. Let's find out. Yeah.
Well, we know it's empty the first time around. So this is,
I hope so.
Add a semicolon here. I'm just going to move my screen controls to the upper right-hand corner.
Do it. That sounds very
And
obnoxious.
God forbid if I actually need that. Okay, so the first time we run it, we get 0 to 4, 0 to 4, 0 to 4. That's what we expect. The second time we run it, we get 1 to 4, 0 to 4, 0 to 4. 0, 0.
Can you make this a little taller? The zoom. Oh, thank you. Oh, it's much taller. The zoom scroll is making that hard. 0, 0, 1, 4. Yep. Oh, okay.
So this shouldn't be there at all, should it?
No.
Because we're actually explicitly removing this corner, right?
Huh? What is it? What is the slice that we expect? So the X1 makes a lot of sense to me. Like we got through that.
Yeah, it's a little bit harder to think about because like we're in a loop, right? There's actually a lot of code that's being run already.
Yeah, but I like that it saw that like X0 was out.
Yeah. If we remove, we have to have at least 3 cuboids in here, don't we? If we just take a cube and remove the corner, the minimum number of cuboids that you would need to compose that is 3.
That's right. Yeah, we're getting like it does the big X volume, and then it's going to do a thin slice of a Y volume, and then a line of a Z volume.
Yeah.
And so it looks like, so what's interesting to me is that the Y volume, it got Y1 to 4. That should be X0 to 4.
Yeah. Okay. So maybe what's going on? I think I have an intuition.
Yeah. Have we like thrown some data out about the axis for rest as we're recursing? We're in the latter case here, right? We're in the.
Well, we do get an overlap. We do get a min overlap on the x-axis, right? That's the first thing that will happen.
Okay. Yeah. Do you want to? Can we step through this? I'd be really curious to see sort of what it's generating. Do we have that ability?
That is a great question.
I feel like what we have is like a strange.
A couple years ago, I had to use LLDB for this. Unix git code LLDB. Yeah, LLDB is what Nathaniel Bumpo is saying.
Alrighty.
Nathaniel Bumpo is a is that Natty Bumpo from Last of the Mohicans? I think that's Daniel Day-Lewis's character name, right? Where do I know that from?
Fictional
Okay,
frontiersman.
yes. James Fenimore Cooper. That is a strong American name. Yeah. Okay. Okay, so now that I got LLDB, what the hell do I do? I can do I need like a launch.json for this? It's not saying anything.
So if you just run, do it.
It says run. Start debugging.
No
shit. There's no launch config.
Oh, okay. Yeah. Nathaniel says, look at his profile pic. Is that a little Daniel Day-Lewis? I got to zoom in on that.
Okay, here we go. I can actually add a launch.json. In order to do this, I actually need to run from. Okay, I think this will work. Add configuration. LDB launch. I mean, that's pretty close to what was there before. Debug unit. Why is this the default? Just debug. Okay, let's see what happens. I'm just gonna like set a breakpoint, and we will see if it. I have very little faith here.
Well, it's trying to call your program.
Ugh. All right, that's fine. I will concede to this. I'll just hard code.
Okay.
Cannot find cargo. Okay, how about I open this specific directory? It's going to be very insistent that I like have the project folder just so. All right, VS Code. Oh, I have to create a launch.json in this directory.
It's directory down.
Yes. Do it. Okay, somehow I knew how to auto-populate. I'm not going to question it.
Oh, that's wild.
Yeah.
Nathaniel Buppo says above the function main, there should be a link to debug the executable.
Right here.
Oh,
I'm gonna click on it. There we go. Okay. And I didn't set any breakpoints, and it ran. So I think we are cooking with gas.
I love it. Hit it.
Which we really should be cooking with electricity, right?
We should be. Holy shit.
All right.
I think you could have just clicked the debug button. Hey, we're there. That's all that matters.
Okay. That's all that matters. Okay. So where are my debugging controls?
Up in the top.
They're hiding behind my chat stuff. Let's give ourselves a little bit more screen real estate. The font size is so big, but you know what? I think it helps people read the code.
I mean, I've got the stream in a window on my computer and it's legible, so it's helping.
Oh, we just jumped over that. That was wrong, right?
What is our split
max
overlap?
Axis is 0. Should I try that again?
What's in our split overlap? I just want to see what it thinks we did.
Yeah, let me go down to this line of code and we'll have it. We'll rerun. Split overlap. Oh, this is nice. This is nice and cozy. Can you believe I've gotten to Advent of Code day 22 without doing interactive debugging? It's all just one line.
I'm impressed.
Max overlap.
So that's right. That's correct, because the overlap is 0, 0, and the non-overlap is after 0, 0. That checks out.
That is correct. Yes, you're
so we
totally
should
right.
be in max. Yeah. Okay. All right. So what do we got in chunk?
Dude, I'm asking that every day.
That chunk looks correct.
That chunk looks correct.
Okay.
But what we really care about, what's rest?
What's rest? Rest is wrong.
Yes.
Well, rest is not wrong because 0, 0 is length 1 here. So is our less than
right? Because we still should be taking out the 0, 0, 0 chunk, right? That the tiny corner piece should still get taken care of in the recursive call.
That's a width 1.
Yep.
This makes it a very hard. That's annoying. That's hard to sort of reason about.
You make one slight tweak to the code.
Okay.
If I don't want to call it rest, what do I call it? What? Foo. I just want to have this on hand.
Mm-hmm.
I can come up with a better name than this. I mean, the reason why I stuck it in the append is because I couldn't come up with a name.
Next.
Next res. Why are you?
Does it need to be
not
mutable?
declared as
Oh,
mutable. Damn it, Rust. Just trying to do easy stuff here. Just leave me alone. Next res. Sorry, I realize we're over time, Dom. If you need to jet.
Oh, I didn't even see that happen.
Yeah.
But I did yawn, which probably means it's late. I wanna see a couple
You
more
want to
steps
see
of
it
this.
through. This is the dedication and stick-to-itiveness that
Well,
makes Dominic Grady who he is.
I want to see a couple more steps and then we'll talk.
I don't think we're screwed, right? I think we've got some subtle bug somewhere.
No, I think it's really close actually.
Yeah. Okay. So should we step in?
We're in.
We're in. Okay. So now we should get an overlap.
What is our overlap?
Okay, we skipped over the x-axis, right?
Okay.
Now this is the y-axis, and we should definitely have an overlap on the y-axis. We should overlap on x, y, and z, right?
Mm-hmm.
And it is a max overlap, just as
Okay.
before. The chunk is what we would expect.
So that is correct actually. Does your volume calculation, when it sees 0, 0, does it add 1?
It does, yes.
Okay. Sorry.
It does 0 minus 0 plus 1. Yeah, let's double check that. That's above. Yeah, it does a minus and then adds 1.
Beautiful. Okay.
So I
that
think
chunk
I
is
see the issue.
Okay, that chunk is 1 unit on the x. Okay. Yeah, what's the issue? Because that looks pretty good to me.
This chunk is going to get added, but 0, 0 is not part of the thing.
Wait, can you say that again?
So this chunk here is what we're saying, and according to the code, is we're adding it to the result. It is like definitely going to be part of it.
Yeah.
But the problem is this is not accounting for the fact that 0, 0 should not be part of like x.
No, it should on this chunk because we're starting at y1.
But this is going to get added to the final result.
Yeah, but like 0 on the x-axis, that voxel is on from y1 and up. Like we've taken out 1 unit at 0, 0, 0 for all 3.
Oh, okay, yeah. I'm not thinking in 3 dimensions here.
Yeah, but x00 is on for like this chunk looks correct.
Okay.
So now what's weird is that we should have had a third chunk.
Yeah. So rest here is
that looks right to me. We should get out of this x00, y00, z14 should be the third chunk added.
Yep.
Let's step in. Yeah.
No overlap on the x-axis. No overlap on the y-axis.
Oh, hello.
Oh.
Wait. No. Run it again.
Unbelievable. You know what? I love programming. That's what it's all about, really.
You were right in Ruby.
I don't even remember what it was in Ruby. 124. That's what we wanted,
that's
right?
That's correct.
That's what we're okay. Let's run it on the real shit, shall we?
Let's run it on their shit.
Yeah. Where's my main function? It's at the very top. Looks like my heart is beating. I'm excited. Really gets the blood pumping.
I love it. This should be.
Oh god. Let's get rid of my debug printing.
Oh wow! Did we like break it for printing far too many things?
It just doesn't. It just runs slowly, right?
Yeah. Oh, you killed it. Okay.
Does that look right?
That does look right, actually. Yeah.
Oh my god! I think it's right. Which means
real input.
I gotta find it again.
We gotta get it again. Yeah.
Dang, son, I can't believe that. I can't tell if it's higher or lower, but it actually looks lower than it was before. But we'll
Well, we weren't removing the entire z-axis for a bunch of shit, so maybe. Let's see.
Oh my god, we got it right.
Okay, so
got
the
it
streak
right.
is preserved. We were off by one character.
We were off by one character. Yeah, so you're counting it. Is that what you're saying?
I am.
Yeah.
I am. Yeah, the points matter here. Cool. Nice work.
Yeah, nice work to you. And Natty Bumpo, sorry for being the last of the Mohicans, but you're also an excellent Rust programmer. Thank you very much for the tips and pointers.
Yeah, thanks for the
learned
help.
a lot from you today. What did we learn today? We learned that I think once again, the wisdom of stepping away from the computer is eternal. You should just, if you can't figure
always
it out,
take a
just
shower.
walk away. Also, having Dom help you program, also a good thing. Yeah, call Dom if you have a programming problem.
That's what I'm here for.
Yeah. He did it for me for free. If you ask nicely, maybe he'll do it for you for free. And then I'm not advertising. I'm just saying that's what I did.
What I learned today
also,
is that Rust's range
it's
function
easy to be
is
off by
busted.
one. Like, see, like it doesn't matter how cool your borrow checker is, or lifetime checker is, or your type checker is. You're always gonna be off by one. It's just gonna happen.
It's inevitable.
Yeah. I am pleased that this ended up being like, after as much as I stressed about it this afternoon, like I'd say relatively straightforward. There's a lot of moving parts, but at least like at every level, you can say, okay, that makes sense. Okay, that makes sense.
Can you log the total number of items in our on set? I'm really curious how many splits we ended up doing with this data set.
Okay. Yeah.
Not for like, yeah. Yeah. I just want to know.
3,948.
That's a lot smaller. That's a lot smaller than I thought it'd be. That's really cool.
Yeah. I think if we did like the let's split everything into the maximum number of chunks possible.
I think it maxes out at 420 by 27 though, because of that constraint, which is not bad, actually. So it's like 11,000 items.
It depends if you only split one prior thing. Like you could theoretically split a bunch of stuff.
You can be splitting multiple things. Yeah. Okay.
But they're not all going to chunk, like they're not all going to necessarily chunk up into like 27 separate things. That's the extreme case. That can only happen to one of them, I think. Yeah. But it really depends on how you write your split function, right?
I like the way this came out. It's really cool.
This is the second day in a row where recursive solution was the right one. There hasn't been as much recursion this year, it feels like, as there have been in years past.
Well, just wait for day 23 to show up in a couple minutes.
Oh, yeah, actually an hour and a half. But you know what? Day 23, I'm going to do it properly on day 23.
On day 23, cool. Yeah,
tomorrow.
Knock it back a day, because then I'll be with you on the 24th and the 25th.
Yeah, you don't want to play hook tomorrow and do it with me tomorrow? I
mean, I'm tempted.
I will let you know when it's happening, and then like if it happens, it happens. If it doesn't, no sweat off your brow or your back or your nose. What's the expression?
Excellent. I think. What is the expression? Nose? No skin off my nose. No skin.
What comes after your nose?
Skin.
No skin off your nose.
Which sounds terrible. Like
I'm not even gonna look up the etymology of that. It's just a weird expression, I think.
It's as so many are. Yeah. All right, cool, dude. All right. That was the stream today. Talk to you later. Maybe see you tomorrow for another one of these.
Take care. All right.
Peace. Are we still on Twitch? We're still.
No, I don't know how to get up Twitch. We're still on Twitch. You know what it is? Because OBS is running on Windows. Okay, now we are about to stop streaming.